starts, we'll go from current slide. Okay. I'll even turn on the projector today. I don't know of any major announcements. I do know that one more student, Julian Wood, showed up right at the end of the class. He had car trouble getting here. But I still haven't seen Justin Charles Burpo or Charles Stephen Hendricks. Now, I know Charles Hendricks has some job problems, so I think he's going to be here. But I hope they got the word the class came back open again, because it had been canceled and then the problem. Wasn't it canceled? Or it was awfully close to being canceled. I don't know if they actually canceled it or not. But anyway, I hope the others show up, because we are into the material now. Any questions before we get started? Okay. And by the way, let me say this. The syllabus is out there on Blackboard now. I don't have my locator card yet. That was one of the phone calls I was making before I came up. I'm trying to get a room number for the class that was canceled, and then they brought back on the Birmingham East Campus. They had already assigned somebody else to the room where I usually teach, so they were trying to find another room for me, but I need to know the room number before I can put it on my locator card where I'll be located. And the secretary didn't know yet, and she was going to try to find out. So hopefully I'll know sometime. Well, I'll know by the end of the day, because I'll be meeting there, and then I'll get that done on the locator card, and then I'll get your locator card out there. The research paper instructions are there. Now, I found out the titles of the tabs. The syllabus is under a tab that says syllabus. Okay, right below that it says instructor information. That's where the locator card will be. It's not there now. Then in the next group of tabs, it's on that same page, next group of tabs it says handout, PPTs, and more. And that's where I have your research paper assignment. There aren't any PowerPoints, but I have the link to the YouTube video there. So you can go back and see last time's class, and you can see classes that are yet to come that I've taught in other sections, other terms. And also I have a couple, I can't think, it seems like maybe 2 links that either I found or students have found and said they found helpful for the course. So I'll put those up there if you need those. All right. Now let me say this about some of those links are book specific, but they tend to be behind. I think one of those has the 10th edition. They didn't have the 11th edition when I checked. They may have it now, but I didn't go back and check it this time, but last time they did not. All right, any questions? All right. Where we had talked about what were differential equations by types, okay? What were the 2 types of differential equations?
Ordinary, partial,
and partial, exactly. So here are a few. Let me get my pen set up. Okay. Dy dx plus 5y equal e to the x. What kind is that? What type? Second, no, these are regular derivatives, so that's ordinary. For it to be partial, you'd have to have that kind of d, a partial derivative, okay? How about this one? d2y dx squared minus dy dx plus 6x is equal to 0. That's ordinary as well. If you have to have the partial for it to be a partial. Now I'm going to go on and start doing some other things too. I'm going to introduce the other. Remember, they're classified 3 different ways: type, order, and linearity. Okay? The type is ordinary, ordinary. The order is what order of derivative it is. This is first order. This is second order. Okay? And then linearity is a little more obscure, but I'll go on and tell you now. As long as anything with a y in it, there's only one of them in each term. Okay? So this couldn't be a dy dx squared. That wouldn't be linear. This is first order. That y is first order. And of course, over there, you can have anything you want to. Those are all things of that. So this is also linear. This one's also, even though this is second order, this is not to the second power. Okay? So this would be a linear, you know, this is linear, and of course, there's no y dependence there. So that is linear.
Does the 2 mean like it's like a second derivative?
Second derivative. Yeah, it's a second derivative. If that was in a parentheses with 2 out here, that would be raised to the second power. So yeah, these 2's here are, and we say dx squared, it's not x squared, it's the dx, you know, you've taken,
The change?
yeah, you've taken with respect to x twice. So they say dx squared. Okay, this one, dx dt plus dy dt is equal to 2x plus y. Okay, we're basically interested in type. What type is that?
Ordinary.
Ordinary, of course. And this is also linear. It's actually linear in 2 variables. You have partials when you have 2 independent variables. This only has 1 independent variable. The y's and x's are both dependent variables. You just have 2 dependent variables. Those only have 1 dependent variable, y. These have 2 dependent variables. So this is still linear, still ordinary, and is linear because each term is only raised to the y's are only to the first power, and the degree is, the order is 1. So it's first order. Okay? How about that? That's a partial, okay? We're not going to mess with partials. I'm not even going to get into the orders and the linearity of that. But this, by the way, you have 2 independent variables, therefore you have to have partial derivatives. You only have 1 dependent variable, that's okay. You can have 2 dependent variables, as long as you only have 1 independent variable, you'll have ordinary derivatives. So this, by the way, is often known as Laplace's equation. You know, if you ever get into a partial differential equation, this happens to be Laplace's equation. Okay? How about this one? D2U. I'm sorry, I said it wrong. Of course, you can tell me the answer right there. Yeah, it's partial. Okay? All right. And this certainly would be second order partial differential equation, though we don't need to know it here. That's also second order. I don't even know if they use the term linearity or not, but these would be, by earlier, what I just told you, would be linear as well. Okay? Because none of your derivatives or dependent variables are raised. You don't have any. You only have 1 term each in each of the terms. In other words, 1 degree term in each of the terms. Okay, first degree. Okay. Okay. And let's see, one more. Okay, and that, of course, is a partial, and that would be a first order. Okay. Partial derivative equation. And for whatever respect, it would follow the term linear as well. Okay, now, these notation that we use with either the D's or the funny looking things are called the Leibniz notation. You can also express these in terms of what they call the prime notation. You probably are familiar with this from your calculus, but just in case it's a little fuzzy or whatever, let's go on and hit these. Leibniz notation is dy, dx, d2y, dx squared, are d3y dx cubed. Okay? That, and it goes on, you can, on and on. Okay? The prime notation would just be y prime, y double prime, y triple prime. Okay. Now, they put comma dot dot dot. I wish they wouldn't. Okay. These follow that pattern no matter how high you go. D to the 15th. You take the 15th derivative, but you could. Okay. These don't follow this pattern any further than this. After this, you start doing, I wish I had put one more, so I'll put one more now. After the third, you put y in parentheses 4. If that was y without the parentheses, that'd be y to the 4th power. That is the 4th derivative of y. Now, the Leibniz notation is a bit better because you know everything you can know about the problem. You know the dependent variable is the y, independent variable is the x. Well, here you know dependent variable is the y, but there's no telling what the independent variable is. A lot of times it is x, it could be t, it could be anything. You just don't know with the prime notation. So that you would have to get from the context of the problem. I'll put my dot dot dots after that because that's how it continues from there. Okay? So anything beyond that, up to the y to the nth. If n is anything greater than 4, it goes in parentheses, and it can keep on going beyond that as well. Okay. So this one here would be the derivative, the nth derivative of y with respect to x to the nth power. Okay. Okay. That's how that would represent. So Leibniz notation just carries the same format all the way through. Prime notation does this. Now, if any of you are really students of Newton, and this is something I don't think they even talk about anymore, Newton did a lot of his things physically, talk about velocities, accelerations, and stuff. So he was always taking, or most of the time taking derivatives with respect to time. So he used the dot notation, okay? And it would be y dot, y double dot, y triple dot. Now, I don't know how many dots he got up to because physically you don't usually go much beyond acceleration would be y double dot, but then there's also, what do they call it? The next derivative is called the, oh boy, jerk, I think, is the, you know, after acceleration, then there's a jerk, and then there's something else. You probably will get to that in mechanics or somewhere. But there's just not that many, so I imagine he used as many dots as he needed, but he didn't need, I'm sure he didn't go past 3. But maybe he did, I don't know. But he used dot notation. No one uses that anymore. Dot would be with respect to time. Prime was then with respect to any other variable. But now we just use primes or Leibniz notation. Okay. Okay. I think I've already hit the next thing when they're talking about, I'll just hit it since it's in the book, d2x dt squared plus 16x equals 0. Okay? Now, in this case up here, x is the independent variable because it's on the bottom. Here, t is the independent variable, x is your dependent variable. X depends on t. Now, and this is an ordinary differential equation, second order ordinary differential equation. Happens to be linear because the independent variable is derivatives to the first power and its derivatives itself is to the first power. Okay? Now this could have been a 16t here if that had been a t rather than x. That is fine, but this then would normally be put over here. Doesn't have to be, but it would normally be put there. Usually keep the independence on one side and dependence on the other when you can. A lot of things you can't, so that's why it's not a big deal. Okay. And they do talk about Newton's dot notation here, and some people derogatorily refer to it as the fly speck notation because it's really, you don't know, is that just a random mark on the page, or is that really, is it a fly speck, or is it a dot, a derivative with respect to time? So, good old acceleration equation, d2s dt squared is equal to minus 32. That would be feet per second squared, by the way, if you're familiar with that. In Newton's notation, that would be s double dot is equal to minus 32. Obviously, Newton was a lot like me, and he wanted to write as little as possible, to get the concept across. So, now, when you get into partial derivatives, so I don't know, this is probably not the best thing to do, but I'm going to do it anyway. Okay. Okay. Whoops. Okay. If this was the partial of y with respect to x, second partial of y with respect to x squared, third partial of derivative of x with respect to of y with respect to x squared, nth partial derivative of y with respect to x to the n. Okay? If these were what you have in the Leibniz notation, you might say, you don't use primes now, okay? Because remember, partials indicate there's more than one dependent variable. So you have to say, oh no, I'm sorry, I said it wrong. Independent variable. So what you have to do now, this would be y sub x, okay? This is y sub xx. This would be y sub xxx, okay? And this would be, I don't know what they do, they just have to keep putting them down there, okay? And then, I don't know how you would express n, you would just have to know what your n was and put that many x's down there. Because with partials, you can have the mixed partials because you have more than one independent variable. So this could be a y sub x, this could have been d2y, partial of x, partial of y, then you would have a y sub y, xy or yx, okay? So you could have different variables down here because this is your dependent variable, these are your independent variables, okay? And since you could have more than one, you could have, say for that fourth one out there, y sub x, yx, or something like that. Just depends on the order that you're taking the derivative with respect to those variables. We're not going to do those, so just so you would have an idea of what it would be doing. There was an equation we did in the first example. Let me go back and do it. I'm going to do it on a clean page here. And again, this almost seems like it's wasting time, but just so you'll be familiar if you ever run into it. d2u d, it's not d, partial x squared, is equal to partial squared, second partial of u with respect to time squared minus partial of u with respect to t. Now, the Leibniz-like notation is very clear in there. What you would do if this were the subscript notation, u, that's the dependent variable, sub xx is equal to what would we go next? U sub tt. Okay, if you have to go, no, never mind. Okay, minus u sub t. Perfect. Okay, so that's how that would go. We're not going to be doing them, but just so if you ever do them, you'll run into it. Okay, so that was classification by type. I've already hit the order, so let's hit the example they give here. It's not the example yet, but the representation they give here. Here's a d2y, back to ordinary now, dx squared plus 5 dy dx cubed minus 4y is equal to e to the x. Okay? What type of differential equation is that? Ordinary, of course. What order? Second order, okay. Is it linear? This is linear, but this one's not, because it's not raised to the first power, it's raised to the third power. The y involvement here, whether as a function itself or derivative of y, is not to the first order. So this would be a third, not order. It's nonlinear. That's all we say, it's nonlinear. That would be linear in partials, or if you went back and changed it to ordinary. This would be nonlinear. Still ordinary differential equation, still second order differential equation, but now it's no longer linear. So linear is either yes or no, linear or not linear. Okay. All right. Now, sort of a weird thing of nomenclature here. We call them differential equations, but most of the time we write them in derivative forms, not differential forms. Remember back in calculus, you did a little bit on differentials, right? Differential is when you split up your dy and your dx, you put one on one side and one on the other. That would be differential forms, okay? But these are derivative equations, you would say, but I guess they got to call them differential equations. You can actually have them in differential forms, a differential equation in differential form, such as m sub xy dx plus n sub xy dy is equal to, they say 0. Doesn't have to be, but it is. Okay? That is a differential equation written in differential form. You separate your dy dx. Now in this one, who can tell what the independent and the dependent variables are? You can't. Okay? That's why I had to stop and look, because if they had done the y here and the x there, then I would have said pretty confidently it's probably dy dx is the derivative form, but in this way you just can't tell. And there's going to be a whole class of differential equations we'll do from this format, okay, and do all our operations there. Because you see, there's nothing indicates which one of these is independent, which one is dependent, nothing there, nothing there, nothing there, so you just don't know. So, but that's in differential form, okay? So, why they stuck that in here, I'm not really sure, but it's not, that obviously would be, I can't say obviously, can I? The only thing obvious is the first order differential equation. Okay? It's ordinary, you can say that for sure, and it's first order, but you can't tell whether it's linear or not because you don't know if this function has, you don't even know which one is the independent, is the dependent variable, and you don't know if either of those functions have it to multiple powers. So we're kind of stuck on that one as far as it is first order though. You can tell that, and that may be why they put it here. Let's do example 2, which is again sort of just a show and tell type thing. But here we're going to assume that y is the dependent variable, okay, of a first order ODE. What does that stand for? Okay, ODE is ordinary differential equation. Perfect. And then kind of the connection between the prime notation and the dy dx is equal to y prime. That's just the definition of what we mean by y prime, right? So, what if we did this? You could write this, maybe I'll do it this way. You could write this as dy is equal to y prime dx. It looks an awful lot like you multiply both sides by dx, doesn't it? Okay? And really, you didn't, because that is not a numerical value. You can't multiply symbolic value, but that sure is what it seems like, and most of the time we'll talk about it as if that's what you're doing. But in reality, you've just written a derivative form into a differential form, okay? And that's exactly, since these two are equal, that has to be true, okay? Now, so remember we're going to have y dependent, x independent, or whatever your other variables will be. I guess it's all x's here. So, what if you had this? Y minus x dx plus 4x dy is equal to 0. Now this is one like that last one we did before. M of xy dx plus n of xy dy is equal to 0. That's exactly this form. Now we just know what the m and the n are. Okay. Can you tell me what order that is? First order. And it's, of course, ordinary. Okay? Now, how would we write that as a derivative form of the differential equation? What would that be? Remember why your dependent variable. Divide by the dx. Even though that's an operator, not really a number, you can even divide this by dx. That's all legal in most states. This is 1. Okay, it'll come back. Yeah. Sometimes if I jiggle the screen too hard, it flashes off. So this would be y minus x plus 4x dy dx is equal to 0. And if you didn't like writing it like that, you could rewrite it as 4x dy dx plus y is equal to x. Okay? No big advantage of that except what we're going to be doing later. We will want to do that. Okay? And yet there is another thing you could do, and later we will want to, but you can handle it either way, is you could then divide everything here by 4x. Now you don't have to, don't worry about this. This is way beyond dy dx plus y over 4x is equal to 1/4. Okay. This, that, all represent the same differential equation. Okay? Now you might want to argue and say, in this form, there's no reason to say that x can't be 0. Whereas in this form, you have to say, no, x cannot be 0. Okay? But see, if x were 0 in this form, you just have a y minus x dx plus 0 is equal to 0. So y minus x would better be 0. So you don't have much of a differential equation left. So still, x can't be 0 in that one either, if it can't down here. But these are all equivalent forms. But this is how you go from the differential form to the derivative form, and then you can manipulate the derivative forms any way you want to. The reason I did this form here is the one that's more clearly, before I divided by 4x, is a linear form. Okay? This is to the first power, that's to the first power. Who cares what's out there? Okay? But this is also, this way, on here you have the leading coefficient of 1. And that just makes, later we'll be trying to get things into this form to solve it by the linear method. Okay, so that's why I showed you that. We will need it in the future. We don't need it yet. Okay? Now, let's go the other way. All right, here we have a 6xy dy dx plus x squared plus y squared is equal to 0. Right? There is a differential equation. All right. Now, that's in derivative form. By the way, what type is that? Okay. The order is first order. What type? Oh, you said it, I think. Ordinary. Yeah, okay, I'm sorry. My hearing's bad. Okay, it's ordinary. It's a first order, meaning the derivatives, first derivative is the maximum derivative you have. Is it linear?
Yes.
Second? No, because here you have a y term and a y term multiplied by each other, and here you have raised to the power. So that's to the first power, that's to the first power, but you got two in the same term, so that's actually a second power, you might say, and this is obviously a second power. Okay? Unless there's something we can do to change it, which I don't think we can, but that's not what we're interested in here. How do we get this into differential form? Not divide. Multiply by dx. You remember, in differential form, you want to get this out of there. And most pure mathematicians would cringe to hear you say that, but the book uses that term too. So you call this 6xy dy plus x squared plus y squared dx is equal to 0. Now you have it in differential form. Okay? Now, I was going to say, if you wanted to try to see if you could get this to be linear, you could divide every term on top by y, because that was the problem here. Okay? Well, this then becomes linear, because you only have that. This becomes linear, but now you have, that one's not linear because you have a y to the minus 1. And to be linear, it only has, the only place you can have a y or any derivative of y is to the first power. You can't have any cross terms. So no, you can't make that one linear. We haven't gotten there yet, but just show you can. Okay. Now, here's some other notations they use just for you to get an idea. Okay? An nth order ordinary differential equation can be written in one dependent variable. That's important here. Nth order differential equation in one dependent variable can be written like this. Capital F, remember we did those in Cal 2, or maybe actually Cal 1 when you're doing antiderivatives. This is not quite the same thing, but it's just another way of expressing. Okay. Some function of x, some function of y, some function of y prime, dot, 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 up to, since you're going up to the nth order differential equation, it would be y to the nth. The nth derivative of y is equal to 0. Now that's one way of expressing the most generic way of any old differential equation you might have. Nth order differential equation. Now look at this, all you can tell is ordinary, because you don't use the prime notation with partial. So all you can tell this is ordinary, and you can tell it's nth order. Okay, you can tell those two. No way you can tell anything about its linearity, but we haven't even gotten there yet. So this would be the most generic way to express an nth order ordinary differential equation is like that. Okay? Most of the time, we don't, though. Okay? We would express it something like this. If the maximum order would be n, we would say d, now this is back in Leibniz, so dn dx to the n, if x is your independent variable. We'll come back in a second. There we go. Okay? Then this would be some little f of x, xy, y prime, dot, 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 up to y to the n minus first derivative. Okay? Now, these may be equivalent differential equations. This one has all of your derivatives incorporated as a function with a capital L, and this one is 1 degree, quite well, 1 order less here. Your F is an n minus first, but see over here you have your nth order. So this is your nth order derivative, the thing that's represented by this term here. This could have been written exactly like this. You just move that to this side and plop everything else into this function. And it's not just moving them there, because if this had any other things done to it, like multiplied by it, then you'd have to be dividing by this. So this is not strictly the same as this, just by adding or subtracting. It could also be multiplied, divided. It's a completely different form. The F's are somehow related, but not any direct relationship like derivative or antiderivative. Nothing that simple. Okay. But they have to be somewhat. Okay. Now, this is called the normal form. Okay, I don't know what they call the previous one. The best I can tell, I've got my pen caught around my tag here. What did they call it here? General form. Don't worry about that kind of distinction. Later we'll be calling something else a general form too. So don't worry too much about it, but just this. So when it suits our purposes, isn't that a clever little caveat? We will use the normal forms. We'll usually say dy dt, if this is a first order ordinary differential equation, will just be some function of x, f of x of y. Okay? Or y d2 y dt squared is equal to some function of x, y, and y prime. Okay? Or you could put dy dx there. To me, it's just sort of creepy to be mixing the Leibniz notation on this side with the prime notation on that side, but the book does it all the time, so get used to it. They mean the same thing, so, well, that's dy dx, not 2y dx. Okay. So, let's look a little bit at normal forms. Again, this seems to be a lot of blah, blah, blah about some stuff that I don't see as all that crucial, but they seem to want to spend time with it, so let's do it. Okay? So here we have 4x dy dx. There's a y there, it's a pretty ugly y, plus y is equal to x. Is that in normal form? Once you can see it again. Oh, this time, oh, there we go. I don't know what's, okay. Is that in normal form? No. How would we get it in normal form?
Multiply the dx.
Okay, no. Normal form has your derivative on one side and everything else on the other side. Okay, you can subtract y from both sides, and that will give you 4x dy dx is equal to, that adds a 0, equal to x minus y, if I could write. Okay. And then what? Yeah, divide by 4x, both sides by 4x. Everything on both sides by 4x. And then that would give you dy dx is equal to 1/4 minus y over 4x. Not that that's any better way, or could actually be written as 1/4 times 1 minus y over x. Or, I mean, you can do anything to the right-hand side you want to. It just needs to be a function of x, function of x and y. Okay. So here's your. This would be some function of x's, y's, and any derivatives less than this, which you don't have any. And constants can be thrown in there too with the x's. Okay. They write it as, and this is how I was going to write it, but decided not to, x minus y over 4x, which is maybe what you were saying when you said divide both sides. So that's it. It's some function of x's, y's, and that's all of this, x's and y's. Okay. You don't have to have them separable or anything else. Now, they call it the normal form. I'm not really sure why. I don't know what's all that normal about it. When we were if we were going to do this as a linear differential equation, which it is, that's a linear differential equation there, we would just divide by 4x, okay, and leave this term right where it is, only divided by 4x, and then that would be a 1/4 on that side. But we won't go there yet. We haven't even talked about linear yet, okay? Now, the B one here in the book is wrong, okay? I don't know which way they intended, but it is wrong. And by the way, y'all have to help me watch out for time. I get somewhat carried away, and so don't let me go too long. I know we have plenty of time left now, but I forget to look at the watch. Okay. So let's do the B part here, and since it's wrong, I'm going to take all the paper I need here, or white space I need. Y double prime minus y prime plus 6 is equal to 0. Okay? You tell me what that would be in normal form. A little out of.
Would it be D2y?
Yeah, you could leave it in prime notation if you want to, though. Okay, a little out of my hearing's bad.
Y prime minus y prime equals -6.
Okay. Okay. Normal is isolate the maximum.
Y prime equals
Y double prime
y double prime equals y prime
minus 6. Okay? Now, in the book, they have it as minus 6y. Now, I don't know if the y shouldn't be there, if the y was supposed to be up here, but one of the others had to be true. If the answer they give would have required it to be a 6y up there, the one they gave you would not have had a y in the answer. So I don't know which of those they meant. And it's hard to tell. That was the original one, and what you said was true. Y double prime is equal to y prime minus 6. But if they meant that to be the answer, then they would have needed a 6y up there. You would think, this being the 11th edition, they would catch, unless they just put this problem in with an error in it. You would have thought they would have caught it by now, but they didn't. But that's all they did. All right, and finally, now we get to classification by linearity. Now, I've already basically given this away, okay? An nth order ordinary differential equation is said to be linear If that capital F, remember when we had that, you put everything inside one thing and have 0 on the other side, okay? If that capital F is linear in all the y terms, y prime, y double prime, y all the way up to the y to the nth derivative of y. It has to be linear in every term. That means an nth ordinary differential equation is linear when I'm going to write this down. Okay. A sub n of x, that's a coefficient function of x, dn, the nth derivative of y with respect to x to the nth, plus some a's. And by the way, and this is just like we did at polynomials, this n is somewhat, I don't want to say meaningless, it's just indicating this is the coefficient function that goes with that derivative. That's all it stands for. It's the coefficient function that goes with that. This is important. That's the order of the derivative. This just means this is the function that goes with that. So this n is just a marker. That n is integral to the whole problem. This means this is the coefficient function that goes with that. So the next function would be a sub n minus 1 of x. D to the n minus first, the n minus first derivative of y with respect to x to the n minus first time. I don't know. They don't put the parentheses in there. I'll tend to want to. It's not a requirement, but it's just so easy for me to lose track of whether that's a superscript or a subscript. But I'll put it the way the book does, okay? And I like to usually put more terms than that one, but they take so much room to write. I'll do one more. A sub, this one is, no they don't. They don't put parentheses there either. To me it's a little clearer with them, but I'll do it this way. A n minus 2 of x d to the n minus second derivative of y with respect to x to the n minus 2 plus, now I'll put the dot, 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 okay, until you get down to, I'm going to do one more than they do, a sub 2 d2 y dx squared plus a sub 1 dy dx plus a sub 0 y plus, no, they put this on the other side. Whoops, wrong thing, sorry. Okay. Now this is how they quite often write a higher order differential equation. They put all the y's, anything that has to do with the y on this side, anything that's strictly x over here. Now there's x's over here, it's scrambled all over the place, and I forgot to do this, sorry. Let me. Should have put this in. This is a2 of x, a1 of x, and a0 of x. Okay. All these terms can have x's in them or not. It doesn't really matter. But that one is one that doesn't have a y in it. It may be a 0. It could be any kind of complicated thing. But that's all the ones with no y affiliation at all. They get on the right hand. So this is sort of the standard way to write a higher order ordinary differential equation. Okay? Now this is linear if none of these y terms are anything but the first power. That includes cross terms, like you couldn't have a y times the second derivative of y with respect to x squared, because then you have two y terms in here. So that would not be linear. But if this is the only y term there, it's not raised to a power, not multiplied by any other derivative of y or y, then that's a linear term in every one. And this can't have any other power either. It can't have a minus power, it can't have a fractional power, it can't have a multiple power. The only power it can have is 1. And that's what's true with every one of these y terms. And you can't have any cross terms in the same term. In other words, a y times a y prime, or something like that. So this is a linear, nth order, ordinary linear differential equation. Okay. That's how they usually write it. Okay. Now, two special cases, I don't know what makes them special, is the linear is the first order and second order. The first order would just look like this. Okay? Throw away the rest of it. This would be a1 of x dy dx plus a0 of x y is equal to g of x. That's your first order ordinary linear differential equation. Your second order would be come on. Okay. This part. Okay. A2x. Forget the third derivatives and anything higher. This would be that part. A sub 2 of x, second derivative of y with respect to x is a sub 1 of x dy dx plus a sub 0 of x y is equal to sub g of x. That would be your, they say these are your two important special cases. Linear first order and linear second order. Nothing's quite obvious about what makes them so special. Okay. Okay. Now, here are the two conditions, and I've been saying it. Maybe I should write it out, but I don't have much room. So what I think I'm going to do here is erase the stuff at the top, just so we'll have everything on one page here. Should have cleaned the page before I went to this, but okay. All right. The dependent variable y, this is bullet 1. Dependent variable y and all its derivatives y prime, y double prime, y triple prime, y the fourth derivative of y, dot, dot, dot. All those higher order derivatives up to y, the nth derivative of y, are of the first degree okay. So the power of each term involving y is 1. This is what I've been saying. Power of each term involving y is 1. Now, they haven't explicitly said this yet, but I want to emphasize this also means you can't have cross terms. You can't have the fifth derivative times the third derivative or any other thing. They can only show up once in one term and only be to the first power. Not fractional powers, not multiple powers, no other powers other than 1. Okay? Now, the second part here, second bullet here, the coefficients, I want to call it coefficient functions. Okay? These are your A's. A sub 0, A sub 1, A sub 2, all the way up to A sub n. Okay? These are the coefficient functions of your y prime, y double prime, up to y, the nth derivative of y, okay, are at most, depend at most on the independent variable. I want to say only on independent variable x, okay? So those coefficient functions can't have a y buried in them somewhere. None of them can. Because if they did, or if they had a derivative of y in them, then that would make them that. So I guess when you combine this one and that one, then you don't have to say, have a caveat there that you can't have any cross terms. Because if you say the coefficient functions can't have any y dependence anywhere in it, only x dependence, that eliminates the possibility of having a y in here or y prime or something like that. So, that's the requirement for linearity. Okay. So, a nonlinear ordinary differential equation would not fit this. Either has a derivative or y to the multiple power or a fractional power or some other power other than 1, or the coefficient function has a y somewhere messed up in it. If either of those happens, it's not nonlinear. Okay? So let's look at a couple of examples. If I can get my pen to come back. There it is. Okay. Cursor to come back. Okay. Y minus x dx plus 4x dy is equal to 0. Okay? Let's just do that. Okay? Now, can you tell just by looking at that whether it's a linear differential equation or not?
Well, they're all to the first power, aren't they?
Say again?
Aren't they all to the first power?
Okay, it is a first order. We can tell that, yeah. It's first order and it's ordinary. We can tell those two things. Can you tell me if it's linear or not just by looking at it like that? I have a few problems. So I like to do something like what we did before. Let's first get it in derivative form. Let's divide everything by dx. And that will then, I'm going to rearrange the order here. 4x dy dx, right? I've written that first, okay? And then we'll have a plus y minus x is equal to 0, right? Because here the dx's go out. Now looking at that, you can move the x over here. 4x dy dx plus y is equal to x. Yes. This term involving a y, first power. That term involving a y, first power. That term over there with no y's, doesn't matter what it is. The coefficient function here, 4x, fine. Depending only on x, no y's here. Coefficient function here, 1. That, no x, no, nothing but, not even an x in that. So yes, this is a linear. Looking at that, not too sure until I wrote it in this form. Now, if you can look at that and say, yeah, I'm pretty sure it is. It is, okay? Because your y is only to the first power and your dy is only to the first power. So you're pretty sure that's going to be the case, okay? How about this one? Y double prime minus 2y plus y is equal to 0. Now again, I think this is a misprint, okay? Why would you write it like that? I think they meant this to have a prime in it. That would be a linear, ordinary, for a second order differential equation, right? Okay? Because Every term with a y in it is only to the first power. Second order, first order, zeroth order, and over here there's no terms at all. Now, if it was as it was written, what I would do is then combine these two and say y double prime minus y is equal to 0, and that's the same case. But why write it as minus 2y plus y? I think that was supposed to have a prime in it. But either case, either way, it would be a linear differential equation. Okay, how about this one? X cubed, d cubed, d3y dx cubed plus x dy dx, pretty ugly writing here, minus 5y is equal to e to the x. Okay? Linear or not? Okay, first, what type of differential equation is it? Ordinary. What order? Third. Is it linear or nonlinear? Why nonlinear?
It's x cubed.
Of what?
X cubed.
Okay. X can be anything it wants to be. This is just some function of x. You couldn't have an x cubed y times this. That would be nonlinear. But if this is only a function of x, no matter what function it is of x, it could be a log x. It could be any function of x. As long as it's only x, it's perfectly fine. Okay? The only terms that have to do with y are only to the first power. Third derivative of y, no second derivative of y, no problem. First derivative of y, only to the first power. Y is only to the first power, so this is linear. The x doesn't matter. That could be e to the x. It could be anything there. As long as it's pure x's, only a function of x, no problem. Just can't have a function.
So it was x cubed y.
X cubed y, nonlinear. Exactly. But x cubed, x to the 4/3 power. It doesn't even have to, x to the minus pi power. It doesn't matter as long as it's only x. X to the minus pi x power. As long as it's only x is there. Now, what I'm saying, some of these are transcendental equations that you may not be able to solve, but they would still be linear. Okay. Make sense? Okay. All right. Now, here's another one. One minus y times y prime plus 2y equal e to the x. I don't know why it does this. I think I have a short or a bad connection somewhere in there, and when you wiggle the screen too much, that somehow, because this plugs in close to it, it breaks the connection. It flashes off, it flashes back on. I don't know. Pain in the neck. They said it would cost more than the computer to get it fixed, and I like my tablet, so I don't want to get rid of it. All right. Linear or nonlinear? Okay. Ordinary or partial? Ordinary, yeah. The prime notation only is ordinary. What order? First order, okay. Linear or nonlinear? Nonlinear, because here you have a cross. You have a y times a y prime, okay? And there's not going to be any way to get rid of it. If that was just y times y prime, then you could divide the y out here, here, and here, flip these two, and then it would be that. But with a 1 minus y, no way in the world to get rid of that and not have it be nonlinear. So yeah, this is definitely nonlinear. Okay? d2y dx squared. It'll come back. Plus sine y equals 0. What type? No, yeah, what type? Ordinary. What order? Second. linear or nonlinear? Second? Sine is not a linear function of y. This has to be first order. See, this is definitely not linear. Okay, it's not a linear function of y. It's some other function of y, but not linear. Okay, so no, that would be nonlinear as well. Okay, d4y dx to the fourth plus y squared equals 0. Height? Order? Fourth? Linear or nonlinear? Nonlinear, because this one is not an exponent, not a linear function of y. It's a quadratic function of y. No way to undo that. Okay. Now we get to a definition, and since Carlton doesn't have a book yet, let me write it out. And were you able to pull up the book? Okay, all right. Here's a definition of a solution of an ordinary differential equation. Okay? Any function, I abbreviate functions like crazy, any function phi, why not f, I don't know, defined, reading like crazy, on an interval I, see, they don't have a comma there, so let me take it out, and possessing, I don't know how to abbreviate that so it makes sense, at least n derivatives, it'll come back in a minute, that are continuous on I, which when substituted into an ordinary and nth order ODE, I'm not going to write out that, ODE, ordinary differential equation, reduces the equation to an identity is said to be a solution of the equation. Of the equation on the interval. Okay. Now, blah, 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 blah. Okay. What is required here? Okay. First, you have a differential equation. Okay. It's an nth order ordinary differential equation. It doesn't say whether it's linear or not, but it says it's nth order ordinary differential equation. If you have a function defined on some interval I, and if it's an nth order differential equation, it's got to have at least n derivatives that are continuous on that I. Okay. What would be some things that would disallow that? If a derivative of this happens to be 1 over x, derivative of log x is 1 over x, that wouldn't be continuous on any interval that contains 0. Okay? Of course, log x wouldn't be on any interval containing 0 or negative numbers. So you'd have to have your interval out here where all the derivatives are continuous, those n derivatives. The n plus direct derivatives may not be continuous there, but all the first n derivatives must be continuous on that interval I. So that's one thing. So when you substitute this function into the nth order ordinary differential equation, you take its first derivative, its second derivative, its third derivative, its fourth derivative, up to its nth derivative. All those are continuous on that interval I, and then plug them into that ordinary differential equation where they belong. If that reduces that equation to an identity, 7 is equal to 7, 0 is equal to 0, something that's obvious, t is equal to t, or whatever, is said to be a solution of the equation on that interval. Now notice your articles, those little words in English, those articles are important. It's a solution. It doesn't say it's the solution. You could have other solutions. In fact, you'll typically have, quite possibly have n solutions, okay, on an nth order differential equation. And not only that, but any linear combination of those n solutions will be a solution. So you'll quite often have an infinite number of solutions. And so that's why this little a there is important. It's not the solution, it's just a solution for that nth order differential, ordinary differential equation. Okay? So if you've written your differential equation in the general form, remember that one, f, capital F of x, and since your solution is phi of x, phi prime of x, all the way up to the nth derivative of phi of x. Yeah. I usually like to use brackets here because we've already used parentheses, equal to 0 for all x's on I. Your interval is I, all x's that are in the I. Okay? It satisfies that equation. We say that phi satisfies the differential equation on I. For our purposes, we'll also assume that the a solution phi is a real valued function. We're not getting into complex numbers in this course as your functions anyway, and as solutions. Let me put it that way, as solutions. We will hit some places where we would, and then we're going to use Euler's equations, other things like that, to get rid of the complex solutions, to write them in other forms. So it says for our purposes, we'll assume that these are all real valued functions. These phis are real valued functions. So remember, I don't know if you remember this from last time, we had y is equal to e to the 0.1 x squared, okay? And we found that to be a solution. Notice a solution, not the solution, a solution to this differential equation. dy dx is equal to 0.2 xy, okay? Now they didn't, and this really bugs me about this book, but I haven't found another book that doesn't do it. They do all this time telling you this is the solution of that without telling you how they got the solution. They wait until chapter 2 or later to finally get around to saying how. They right now say, oh, this is the solution to that. Well, how do you tell? Well, you take the derivative of that and plug it in, and you'll see it comes out to that. You know? So to me, we ought to be solving them, not just showing, oh, this is a solution. Okay. And the interval on the interval minus infinity to infinity, because this function here, start taking its derivatives, they're all real valued solutions. None of them have any holes in the graph, discontinuities, or anything. They're all continuous solutions as long as you want to take them. Okay. Now, occasionally it would be convenient to denote a solution by the alternative symbol y of x. And that was my question. Why didn't they use y of x to begin with? Why did they introduce phi of x? I don't know. So, all right. Now, let's talk about the interval just briefly. You cannot think solution of an ordinary differential equation without simultaneously thinking the interval over which it is the solution. And if you think in these terms, the domain over which that solution makes sense, and it has all its derivatives of value. So you can either talk about the interval or the domain of the function. They mean the same thing. The interval in the definition that we just wrote, that one right up there, is called the interval of definition, the interval of existence, the interval of validity, or the domain of the solution. They use all these terms, blah, 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 to name the same thing. If it's the interval or the domain, to me, just leave it to those two. And it can be an open interval on AB, like this, meaning it's all the numbers in between A and B, but not necessarily A or B. It could be a closed interval, AB. That means it's everything in between plus the endpoints. It can be half open, half closed, or whatever, or it could be, say, anything from A to infinity. So it may not have a limit on one side, but it does on the other. It could be a closed open on the A side, or it could be minus infinity up to B, either open or closed there. Either one, any of those could be. So usually it'll make perfect sense, and it'll be fairly obvious. I can't find my cursor. Do you see it floating around anywhere? Where is it? It's where?
Above the infinity.
Oh, I see it now. I couldn't see it on this screen, but I can see it there better. Okay, so let me get here. Let's do example 5. Okay. And this is mostly what we're going to be doing in this chapter. Not finding a solution, verifying a solution. Verify that the indicated function is a solution of the given differential equation on the interval minus infinity to infinity. So our interval is minus infinity to infinity. I can't write very well. Okay, I'm stuck on my tag again. Okay, here's a differential equation. dy dx is equal to xy to the 1/2, and the function y is equal to 1/16 x to the 4th. Okay? How would you go about verifying the second thing there is a solution for the first thing?
It's saying that, okay. Did you just plug it in?
Basically, yes. What do you mean by plugging it in?
So if you get y equals 1/16 x to the 4th, would you just put in y on that?
Okay. So what would be your first step to show that?
X times 1/16 x to the 4th.
Okay.
Square rooted.
All right. Okay. All right. Say again? Okay. Both of what you're saying is correct. It doesn't matter which order. Let's take a derivative, y prime, or let's keep the same notation, dy dx, okay? Get rid of the prime there. So take a derivative of this, and what would be its derivative?
1 over 4
1 over 4
times x to the 3.
x cubed. Is that what you said? Yeah, Perfect. Okay, that's all you need to do there. But then the other thing you said, you also need to find out what y to the 1/2 is, right? Because you have that over here. What is y to the 1/2? The square root of y, which is the square root of 1/16 x to the 4th. And what would that be?
That'd be 1 over 4 x squared.
X squared. Perfect. Okay? Now, let's plug in these things to that original. The dy dx is 1/4 x cubed. Now, this is a question mark here. Is that equal to x times 1/4 x squared? Yes, pretty obviously it is. So 1/4 x cubed is equal to 1/4 x cubed. An identity. No ambiguity. Now, and is it true on the whole interval? All real numbers. Okay? The only little bit of a possible problem here would be that y couldn't be negative, right? You can't take the square root of a negative number. But if this is true, y is equal to 1/6 x to the 4th, y is never negative. It could be 0 when this is 0, but you could take the square root of 0. But any other x you put in there, positive or negative, when you raise it to the 4th power, it's always going to be positive, so y is always going to be positive. So yes, this is true everywhere. Negative infinity to positive infinity. Remember, this is the interval of your x's, not your y's. It's the interval or domain of the x's, the independent variable, not the y's. The y's here are always positive, so you can do everything in that problem. Okay? So that wasn't too bad, was it? Okay. All right, there it is. Let's erase again. Y'all got it? Okay. Don't let me erase something you're still puzzling about. Okay, here's the second one. Y double prime. This time they're using prime notation. Minus 2y prime plus y equals 0. There's your differential equation. Ordinary, second order, linear differential equation. Okay? Here is your proposed solution. Y is equal to x e to the x. Can you verify? And by the way, that function there is valid for all real numbers. X is valid for all real numbers x, and e to the x is valid for all real number x's. And the product is valid. So the interval seems okay, so far anyway. So what would you have to do to verify that is a solution for that equation? Take a derivative, okay? Now, usually in my Cal 1 class, I'll tell this dumb story sometime, or it's not a story, it's just a phrase. Usually that's a pretty good thing to do. In Cal 1, once you find out what a derivative is, then most of the problems you're going to deal with, not going to be a bad idea to take a derivative. And I say this, and I hope no one's offended at it, but I've been to several churches that have what they call children's church. And it seems like just about all the time when they bring all the little kiddies to the front of the church, usually then the pastor or some big honcho up there is going to be talking to the children. And they'll usually start off by asking them some question. Now, of course, the kids are there, you know, with just panicked about what you do in front of all these people, your parents and everybody else out there, and ask a question. And you don't know, have a clue what the guy's talking about. So usually some little boy in the back will say, Jesus, figuring that that's not going to be a bad answer in church. You know, that no one's going to argue that Jesus is the answer, right? You know, so I call this the Jesus answer. You know, when in doubt, just take a derivative. It may be the best thing to do. In this case, it is. So let's take the first derivative, and what would that be?
It
Say again?
X squared e to the x.
Well, wouldn't you
No,
have to
you're
do the product rule?
you're taking. Okay, yeah, product rule.
So that's gonna be e to the x
E to the x
plus x e to the x.
Perfect. Okay, you see it? Remember that? First time derivative of the second plus the second time derivative of the first, right? Only you did derivative the derivative of the first times the second plus the first time derivative of the second. Yeah. Okay. What's y double prime?
E to the x.
E to the x. I can do that one. Okay. Plus
e to the x
e to the x plus x e to the x. Okay, got it. So this could be written as 2e to the x plus x e to the x. Or it could be written as 2 plus x times e to the x. I don't care how you write it as long as you write it correctly. Okay? And I really don't care which form you leave it in, but let's go back and plug now. Okay? I think probably the second form is going to be the best here. That's your y double prime. Is going to be 2e to the x plus x e to the x minus 2 times your y prime, which is e to the x plus x e to the x, plus y, which is x e to the x. And the question is that equal to 0? We don't know it yet, but let's see what happens. It'll come back. 2e to the x plus x e to the x minus 2e to the x minus 2x e to the x plus x e to the x. Is that equal to 0? Well, let's see. Here we have a 2e to the x minus 2e to the x. Those certainly had to be 0. They go away, right? All right. Here we have an x e to the x, another x e to the x. That gives you 2x e to the x minus 2x e to the x. Sure enough, that adds a 0 as well. So you get 0 equals 0. Yay, team. Okay. Yes, that is a solution to that differential equation. Notice, not the solution, just one of many possible solutions. Okay? Good deal. Any questions? Now,
So basically, we're just trying to get them both equal to each other.
yeah, you're trying to see if that solution, when you do these things to it, and plug them back here, this side's equal to that side.
Yeah, we're just verifying that it equals 0.
Yeah, this one is equal to 0. The previous one was equal to, x, y to the 1/2. Yeah, right. Whatever, it makes that equation up there an identity. Okay. Now, and that's certainly an identity here. Now, let's look while we're here. I said that's not the only solution. Here is another one. How about y is equal to 0? Is that a solution? Because y prime is 0, y double prime is 0, and 0 minus 2 times 0 plus 0 is 0. And sure enough, that's called the trivial solution. Okay? All right. The previous one we did was this one. dy dx is equal to xy to the 1/2. Okay? And sure enough, our solution for that was y is equal to x e to the x. This one, obviously, when x is equal to 0, y is equal to 0, so that works as well, okay? So the trivial solution, and this is just something we're going to do a little bit later, a solution of a differential equation that is identically 0 on the interval I is said to be a trivial solution, okay? And both of those had that. Now, okay, how are we doing? Yeah, we've got another 20 minutes, is that right? Something like that. I think that's right. Plus that. 10:45. And what was it now? Yeah, okay. So 30 minutes. Yeah. Yeah, but we were started late, so I can't always go by that. I can't remember what time we got started. Yeah, because remember I did that turn. I usually don't turn it on while I'm calling roll and that kind of stuff. But when I'm making announcements, I try to have it on by then. But we got to talking about whatever we were talking about to begin with. Admirals and all that kind of stuff. So I blew out that one. So that's why I can't trust that. Okay. Or I could just give you 2 hours and 15 minutes of instruction every day, no matter what time we start. We could do that, couldn't we? You wouldn't like that, would you? Okay. One of the reasons I asked, quite often in the morning I rehydrate, and sometimes the old bladder says, hey, I can't wait this long. So if your bladder is the same and you need to take a bladder break, we can do so. So let me know. Don't get suffering in here. And if I get suffering, I'm going to say, let's take a bladder break. Okay, so I was just contemplating, can I hold it for another 20 or 30 minutes, so let's see. All right. Now, the next concept here is that of a solution curve. Okay? The graph of a solution phi of an ordinary differential equation is called a solution curve. And since phi is a differentiable function, it is continuous on an interval I of definition. Has to be, okay? Thus, there may be a difference between the graph of a function phi and the graph of the solution phi. Put another way, the domain of a function need not be the same as the interval of definition or domain of the solution. And that's what this next example is going to illustrate. So, blah, 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 let's just do it. The domain of y is equal to 1 over x. What would be the domain of that? The function, y is equal to 1 over x.
It would just be from positive 1 to infinity. 1 to infinity.
Okay. It can be more than that.
Or negative, it just can't be 0.
It can't be 0. That's the key. The domain of this function y, this is my notation, this isn't standard, is the set of all values of x such that x cannot equal 0.
So technically it'd be negative infinity to negative 1 units.
Okay, no. It's from negative infinity to 0, not counting 0, union that with 0, not counting 0, to positive infinity. So it's not 1, it's 0 is the cut point. So basically it's all real numbers except 0. That's what the first one says. Or everything to the left of 0, but not counting 0, and everything to the right of 0, not counting 0. And if you were to graph this, this is how it looks. Right? Yeah. Not defined at 0. Defined to the left, defined to the right. Stand up, sit down, fight. No, okay. Okay. So it's not, that is the domain of the function. Okay. Now, if you wound up with that being a solution to a differential equation, the odds are it's either going to be on some interval on this side or some interval on that side. but it certainly cannot be any interval that crosses 0, because it's not even defined there. So just because the domain of this function is all real numbers not equal to 0, the interval of your solution is probably going to be strictly on one side or the other. It just can't ever cross that, but it usually won't be both. Usually going to be on one side or the other. So that's what they're saying. When I said before, it's also the domain. Well, it may be part of the domain. It has to be portions of the domain. So here's a differential equation. X, y prime, plus y is equal to 0. Okay? Now, the question is that a solution to that? Is y is equal to 1 over x a solution to that? What would we have to do to determine it? Take the derivative of y. Before I take the derivative of y, I do not like taking derivatives of fractional forms. I rewrite this as y is equal to x to the negative 1. I like taking the derivative of that a lot better. So what is y prime then? Say again?
That's going to be negative x divided by 1, or no, negative x minus 2.
To the minus 2, exactly. Okay? So, let's take that and plug it in here. This will be x times a minus 1 over x squared. I'm going to go back and write it as fractional form again, right? Is that okay? Okay. Plus y, which is 1 over x, is that equal to 0? You tell me. By the way, Nolan, I guess you realize you are the odd man out here. We write with the correct hand. You write with your right hand. Okay. Never mind. I don't know if you noticed that. You're outnumbered. Get used to it. We're taking over. Okay. Okay. What? Say again?
Maybe in baseball.
All right. Is that true?
Yo, left-handed pitchers.
No. I mean, let's get back to the differential equation. All right. No, I agree with you. Well, x times negative 1 over x squared would be the x wipes out an x, and then you have the negative 1 over x plus 1 over x, sure enough, is equal to 0. Absolutely. Okay? Now, but that's not true everywhere. It's only true on an interval. It could be on the interval negative infinity to 1, to 0, sorry. Not 1, to 0. Or any smaller one, like minus 3 to minus 1. Anything such as that. Or it could be from 0 to infinity, or from 17 to 43. You know, it doesn't matter. Anything that's over there in that part. But it cannot be from negative 3 to 1. That will not be a solution there, because number one, the function isn't defined there, and so your solution couldn't be either. You can't do anything where the function is undefined. So basically, if you have to have an interval, it's either going to be on this side or that side. It can't ever be both sides at the same time, because your differential equation is usually defined at some value, and that value must be in the interval. Okay? The interval cannot include 0. Okay? So basically, we usually take the largest you can do, but you can't go any further. Either one side or the other. Okay. Now, here's another thing. We're not going to talk about this too much now, but it's going to show up more later, so just going to get the nomenclature. That's all we're doing now, is just getting our defining what is a solution, what is the interval, what is thing. Well, here's explicit and implicit solutions. Okay, you did this back in Cal 1 when you did explicit differentiation or implicit differentiation. Implicit differentiation is when you couldn't separate the things to get y's over here and everything, all the x's over there. That would be explicit differentiation. When they're all jumbled up together and couldn't separate them, you could do implicit differentiation. Same type thing here, okay? A solution in which the dependent variable is expressed solely in terms of the independent variable and constants is said to be an explicit solution, okay? So let's do the implicit, and that's what the definition here is. So let me write this one down for you then. A relation, and why they use these different things, a relation. Now notice here, by using the term relation, that doesn't mean it's necessarily a function. A relation G, capital G, of x and y is equal to 0, is said to be an implicit solution an implicit solution of an ODE, ordinary differential equation, I'll abbreviate like crazy, on an interval I, provided, I can't write, that there exists at least one function phi, they like phi, that satisfies the relation okay, as well as the differential equation. Okay, now that is a on I. To me, a real nebulous sounding definition. Okay. First, what's the difference between a relation and a function? Anyone remember? Way back. All right. Just increase the class size. Charles is here. Still good by Charles, right?
I hope so.
Good night. Because the first guy that hasn't been here yet is Justin Charles Burpo. And I'm a Charles, you're a Charles, and you're a Tarleton, so again, you're the odd man out. You don't have a C name, do you? No, okay. Again, okay. Difference between a relation and a function has to be for any input, only one output. A relation, you could have multiple, for any one input, you could have multiple outputs. But there's still a relation there, okay? It's said to be an implicit solution of an ordinary differential equation, provided there is at least one function that also satisfies the relation as well as the differential equation. So that doesn't make it any clearer, I don't think, but that's what they're getting at, okay? Now, they give you that definition, and then what do they follow it with? It is beyond the scope of this course to investigate the conditions under which the relation will do this. So, in other words, does it really matter? I don't know. We're not going to do it in this course. But let's do example 7, and maybe that'll illustrate it, if not anything else. Here's a relation. X squared plus y squared is equal to 25. What is that?
Oh, that's a circle.
A circle of radius 5, right? Yeah. Is it a function?
Yeah. Well,
Vertical line test fails. Remember?
oh, yeah. 'cause it
Oh,
goes-
yeah, because you have 2 points. Yeah. So it's a relation, but it's not a function. Okay? But we know what it is. It's a circle. Okay? It says that relation is an implicit solution of this differential equation. dy dx is equal to minus x over y. Okay? Well, let's see if that's true. We need to verify that. So what would we do?
We would take it.
Take the derivative. Yeah, good Jesus answer, right? Okay, Charles has been in my class before. He remembers Jesus answers. What would that be? How do you take the derivative of that?
Would you do partial derivative?
Yeah, you do implicit differentiation.
Uh,
Remember how that went?
yeah. So you do x squared.
No. Wait. Take a derivative.
2x
2x, good.
y
Plus what?
plus y squared y.
Woo. Take a derivative. Chain rule. 2y times y prime. Remember? That's chain rule. Is equal to 0. Very good. Derivative of 25 is 0. Now solve for y prime. That's your dy dx, isn't it? So we'll subtract the 2x from both sides, and that gives us 2y dy dx is equal to minus 2x. And then divide both sides by 2y. And this will be dy dx is equal to minus x over y. Yes. That satisfies it, right?
So should he use the chain rule?
Well, it's using implicit differentiation and the chain rule. You see, this part, 2x, take the derivative with respect to x, that would just be 2x. That's pretty obvious, right? Here, you're taking the derivative of y squared. Well, the outermost function is a square root function, and the innermost function is the y. Okay? So it's 2y, that's the derivative of the outer function, times the derivative of the inner function, which is dy dx. So that's the chain rule. And then we're wanting to solve for this, so subtract the 2x from both sides and divide by 2y, and that gives you exactly that form. So this relation satisfies that. Okay? Now,
If there wasn't, if the y wasn't getting squared, would it just be y prime?
yeah, if the y wasn't squared, that's a very good question. That would then be a parabola, wouldn't it? Up there at 25, okay? That would be a function. Then you would have y is equal to minus x squared plus 25. 25. Where the 4 came from, I'm not sure. Okay, something sick somewhere here. Okay. Then you can solve for that, and then you take a derivative, and y prime is equal to minus 2x. Right. And you could do it that way too, but it's so much easier to solve for y. This is explicit differentiation that's implicit. Okay. And this will be true for all values of x. Okay. This one, not quite. Okay. Certainly, this would not be defined for any value where x is less than -5 or greater than +5, because your circle is inside that, right? So there are certain values you can't have. And this says the y can't equal 0 from our very beginning. So that means even the end of the circle, you have to have an open circle there, open circle here. So it wouldn't be a complete circle. I don't think they draw it that way, but they really should have. Okay. All right. Now, so what we wind up with here is, and if we'd have taken this equation and done like we maybe should have, well, if we had solved it for y, this would then be like we did here. If we had solved that for y squared is equal to 25 minus x squared, right? Take this down, subtract x squared from both sides, right? Okay. Then take a square root. Y would be plus or minus the square root of 25 minus x squared. Well, that means you could either have y is equal to square root of 25 minus x squared, or y is equal to minus the square root of 25 minus x squared. One would have been the top half of the circle, and one would have been the bottom half of the circle. Okay? But in both of those cases, the y can't be 0 because of this. So that's why I had to put open circles here. Your domain here is all x is between -5 and 5. Okay, well, that's true. So I put my axes in here, -5 to 5. Okay, same thing here. Okay, that would be the case, but in both cases you would have to exclude the endpoint. Now I'm not too worried about that part, but you see, this says the endpoint's fine, this says the endpoint is fine, but this says the endpoint's not fine, you know, because you can't, y can't be 0. Okay, so and part of the reason for that is your derivative here can't be negative x over y, because derivative of your endpoint is a vertical line, right? What's the slope of the vertical line? Is it positive infinity or negative infinity? It's not defined, okay, because it's 1 over 2. So for this to be true, you have to exclude the endpoints there. So it's the top half of the circle or the bottom half of the thing, but it's not going to be both. Okay? So looks like it's perfectly fine. There's your equation. But for this to be true, you have to exclude the endpoints, because you have to divide by 0. And I don't know. They show the whole circle, they say, is the implicit solution, and the two parts of it are the explicit solutions, but obviously you can't have both of them, because I don't even see how they could say that's the whole circle is an implicit solution. But anyway, well, that's just those little things to keep in mind. Now, let's talk about families of solutions. I've already said that there's basically an infinite number of solutions for most, if not all, of your differential equations, unless, of course, you know a condition. Now that condition could be an initial condition or any other kind of condition. That may limit and not have you an infinite number of solutions. Okay. I think we're only going to have time for an introduction to this. I don't think we'll get it finished. But let me at least introduce it to you, the concept here. If you remember back when we did integration, especially indefinite integration, in other words, you don't have the limits there, what did you always have to put at the end? Plus C, because it was a whole family of solutions. It could be this solution, that solution, this solution, that solution. Well, the same thing holds for differential equations, only they don't have to be sort of parallel-looking things. They could be a whole variety of different curves in there, but if you know one point, so this one has to be on there, that then identifies which curve you're on. So that's what we're talking about, families of solutions. And I really don't want to draw some of these, so I'm going to hold up the book and let you see them. Poor people at home, if they don't have a book, they don't know what I'm hooking up there, because their screencast-o-matic is going to pick up what I hold in front of the screen. I wish they had PowerPoint with this, but they don't. The study of differential equations similar to integral calculus when evaluating an antiderivative or indefinite integral of calculus, we simply use the constant C of integration. Analogously, we will see in Chapter 2 that we're solving a first-order differential equation, f, this is your general form, of x, y, and y prime. That's a first-order differential equation equals 0. Okay, that's in the general form. We usually obtain a solution containing a single constant or parameter c. Okay, first order, a single constant. Okay. Then the solution f of x, y, y prime equals 0, containing that constant c, is a set of the it seems like to me they put it in the wrong place here. They say if it is a value c where x equals c, seems like to me it should be no, it's not x equals c, it'd be y is equal to c. Seems like it should be g of x, c, and y prime equals 0, but they say x, y, c equals 0. I'm not sure I agree with that yet, but anyway, it's called the one-parameter family of solutions. Oh yeah, I see what they're saying. Okay. If you have a parameter, then the x, y values that give you c as your solution, that will be it. So yeah, I guess what they're saying is right. If you have a higher order, nth order, where f is x, y, y prime, y double prime, dot, 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 up to y, the nth derivative of y, okay, equals 0, then you're going to have an n parameter system. See, this is a one parameter system. Y is equal to c. Find the c, you got which one you have. Here you have an n parameter system. So you have NCs. Some of them could be the same or different, or they could all be uniquely different from one another. That is your n-parameter family of solutions. So then you have G of X, Y, and C1, C2, C3, ... up to C sub n. You have n parameters there, and that will then equal to 0. Okay? And that just picks out one of the curves. Okay? Now, a solution of a differential equation that is free of parameters is it time? Is that what you said? Yeah. Yeah, I was afraid of that. Is called a particular solution. If there is a solution, but it doesn't depend on a parameter. And this is not going to show this, but I'm just going to do it now. This is a family of solutions. You can start over here with the yellow, the green curve here. It's the highest curve on this side, but the lowest on this side. Then the yellow curve is like that. The blue curve is like this. The pink curve is like that. Yeah, and on and on and on. If you have some value, x, y, that you know, this is, say, c is equal to 0 is the blue curve. C is equal to greater than 0 would be the pink curves, the green curves, and the yellow curve would be c less than 0. But each one of those stands for a particular value. Other times it might be a lot more bizarre like this, that you can't really see as much of a pattern there. So they go up, some go down, some do all sorts of things. But if you have a single value c, that will determine which one of these solutions you have. So we'll do that in example 8. So that's where we'll begin. We're not going to hit particular solutions for right now, but we will hit them a little bit later. Okay? So we'll begin next time at example 8. Now, let me also give you some homework exercises. I know you won't want to leave home without that. So last time we really hadn't done enough to get those. We're almost finished 1.1, by the way. You can do any of the odds, 1 through 7, and most of the odd number answers are in the back. Maybe not all of them. Do any of them that they have the answers in the back. I think you can do 9. I think you can do either 11 or 13.
Either or?
Yeah. I think you could do either 15 or 17. Also 19. And hold off on 21 and 23 until later. So do any of those. Their answers are in the back of the odd numbers on most of them. If the answer is not in the back, do another odd number that is in the back. All right, good deal. Okay, I'm going to shut it down.